Hi guys, today we're going to talk about molar solubility. So this is basically how well something will dissolve in another solvent. We're going to use calcium fluoride for an example. So the first thing that you want to do when you're solving a molar solubility problem is to write the dissociation reaction of your actual solid. So since we're using calcium fluoride, or CaF2, we're going to write the ions that this dissociates into. So it starts out as a solid, and then when you add it into a solvent, it's going to dissociate into calcium 2+ plus 2 negative fluoride ions. And both of these ions will be in an aqueous environment. And the way you distinguish what the charges are on the different ions, if it's a fluorine, chlorine, or anything in that row of the periodic table, you're just going to assume that it has a -1 charge on it. And so since you have 2 fluorines, each with a -1 charge, you do 2 times -1, and then we'll get you -2 charge for this part of the molecule. So to balance it and have a neutral charge, calcium has to have the same magnitude of charge with the opposite sign on it. So it has to have +2 on it. And so that's how you get these 2 ions right here. So the next thing that you want to do, so we're actually going to assume that this is in a solution of 0.1 molar, we'll say Na+ or sodium fluorine. So that means that there's already some fluorine in the solution before we actually add our solid to it. So the next thing that you want to do is make a race table. So again, this stands for reaction, initial conditions, your change, and your equilibrium. So you're going to do this for your 2 ions that you have. So you're going to do calcium 2+ and fluorine -. So initially we have 0 calcium, and this is molarity or concentration. So initially we have 0 calcium, but since we're in 0.1 molar of sodium fluoride, we're going to start off with 0.1 moles of fluorine. And then the change is going to be +x for calcium, plus 2x because of the coefficient here for fluorine. And then our equilibrium is going to be x, and then 0.1 plus 2x. So the next step is to write your equation for KSP. So that's equilibrium of solubility, and that's just going to depend on your ions as well. So usually when you write K, it's products over reactants. But because our reactant is in a solid state, its concentration is just fundamentally 1. So we can go ahead and ignore our reactant concentration and just write KSP is equal to calcium times fluorine. And because of this coefficient here, we have to square the concentration of our fluorine. So this should be KSP. The next step is to plug these concentrations in your race table into your KSP. So you'll get KSP equals x times 0.1 plus 2x. Now to simplify this, we're going to make, and this should be squared. Don't forget the squared. So to simplify this, we're going to make the assumption that your x is so much smaller in comparison to your 0.1 mole that if you add any x to this amount, it's essentially just going to stay as 0.1. So we can make the assumption that this goes away. So we get x times 0.1 squared is equal to, we're going to plug this in here, so we'll get 1.46 e to the -10. And then doing that, you'll solve for x and you'll get some value, and we'll do that here now just because I don't have a calculator. But that's basically how you go about solving a molar solubility when you're already starting with an initial concentration of one of your ions. It's simpler when you don't have an initial concentration because you simply plug in x times x equals your KSP and you'll just solve for the square root of KSP, or if you have a different coefficient, make sure you account for that, but there's a little less math involved, so it's a simpler case. So that's molar solubility.